Hey everyone, welcome back to Calculus 1. This is going to be lecture 13 of the course. And in this course we're going to continue with our applications of derivatives by looking at how derivatives can be used to find extreme values on intervals. Okay, so let's call this section 3.1 and we'll call it Extrema on an interval. Okay, so Extrema on an interval. Okay, so let's talk through what we mean here. There's going to be some definition of terms to make sure that we understand what we mean by this word extrema. So, given a function f that will be defined on some interval I, the question what we're faced with here is how might we identify extreme values, like i.e. maximums and minimums on I. So given f defined on I, and we'll see that this is usually thought to be a closed interval, how to identify extreme values. And by extreme, we just mean max or min values on I. Okay, so 1 second there. All right, so given f defined on an interval, how can we identify extreme values? Well, so first of all, let's crank out a sort of more rigorous definition of what we mean by extreme values. And so let f be defined on I containing a point C. Okay, so basically the min is defined to be, so f of C is a min of f on I if fc is less than or equal to f of x for all x in I, except for C itself, of course. All right, and then a max is the same thing, except flip the inequality. So f of C is a max of f on I if f of C is greater than or equal to f of x for all x in I. Okay, so there we go. So this seems all very straightforward, well and good, not a problem. But things can get tricky when the interval under examination is open or when the interval lacks continuity. Okay, so let's take an example here. Let me draw a picture. So let me just write that first. Things can get tricky when the interval is open or not continuous. Right, so if that happens, you can run into some issues. So let's first start with this example. We'll say I equals AB, but I has a discontinuity at x equals 0. This is an example. Okay, so let's see what this looks like. So here's a sample. So we've got a discontinuity at x equals 0, and then it looks like this maybe. And then we'll say A is here and B is here. Okay, so maybe this is our function. So normally the minimum would be at 0, and just kind of take this visual at face value, right? Just assume that it does come down to this nice, this is basically like the graph of x squared or something. And so normally we would say, yes, indeed, the minimum would be at x equals 0. But that point, that one point, x equals 0, 0, is not part of the function. So in this case, you've got a whole bunch of values that kind of come down and get arbitrarily close to x equals 0, but x equals 0 itself is not included in the function. So in a case like this, even though it may seem unintuitive, there is no minimum. On the interval I equals a to b. Right, now this is actually a far more profound concept than you may think at first glance, right? So you may just say, well, wait a second. Okay, what about the point right next to x equals 0? Wouldn't that represent a minimum? Well, theoretically speaking, if you were in fact able to identify the point right next to x equals 0, it would represent a minimum, but that point is not a point you can find, right? And so this has to do with the denseness and the completeness of the real number system. There is no point right next to x equals 0 that you can call the minimum here. So intuitively, it seems like there should be. I can certainly see that the line comes down, down, down. All I need to know is what that last down point is. The problem is 100% in identifying that last point right before 0. So I'll just sum it up, and this is to really get at this in a rigorous way. You need to take a course like real analysis. In that course, you would study things like limit points, and you would be able to see, irrefutably that there is in fact no minimum in this interval. But what I'll say here is, and I'll just put this in quotes, there is no identifiable point right next to x equals 0 that we can use as the minimum. There are certainly no shortage of points next to x equals 0, but to find the smallest one is the problem. Okay, so that's an example where where having a discontinuity kind of throws the presence of a minimum into turmoil. Okay, let's see another example, kind of similar but different, and in this case we'll be looking at an example where the interval is not a closed interval. So let's consider another picture here. We'll just take our x squared function again, and let's say we've got a and b like this, and the function kind of comes down and does one of these. Right, now the issue here will be that we'll say, this is a terrible drawing, this should really be over here. We'll just say that that works like that. So here we're going to take the interval I to be equal to the open interval a to b. Right, so all that means is that the endpoints a and b are not contained in the interval. Okay, they're not included in the interval. So in this case, yes, we do have the minimum between a and b, that's x equals 0. So the min is x equals 0, but there is no maximum. And the reason there is no maximum is the same reason that we just saw in the previous example of why there is no minimum in the case where the lowest point is missing. So here you could say, oh, that looks like the highest point, a and b, if those were those endpoints were included, then clearly those two would satisfy the maximum, the definition of a maximum, but they're excluded. And so theoretically speaking, the maximum is going to be whatever point is right next to a and whatever point is right next to b. And those points, again, are not points that we can identify. We can't just say, hey, it's a minus some arbitrarily small number, right? Because there's a continuum there. There's an infinite number of numbers that are very, very close to a. So for the same reasons, there is no maximum because there is no, and this is the key, identifiable point right next to A and B. Right? There's definitely a point there, but you just don't know what it is. First of all, identifying it would require an infinite decimal expansion, and that in and of itself would be an impossibility. But then also there is a, between any point you identify, there's going to be an infinite number of points between that point and B or A, right? So again, this is a complex issue. And this is the subject of real analysis. A lot of real analysis goes into this in detail, and but suffice it to say, there's no point that we can point to and say, oh, the max is going to be this f evaluated at this point. It just doesn't exist for this interval because of the openness. Okay. So those are kind of like the edge cases that we have to be careful of. So here's a theorem. So if f is continuous on a closed interval AB, so if f is continuous on a closed interval AB, then f has both a minimum and a maximum on the interval. Okay. All right. So if it's an interval that's closed and continuous, then you're definitely going to have a max and a min. Okay. And we'll do some examples in a moment to talk through that. But let's define what we mean by a relative max or relative min. So if there is an open interval containing C, on which f of C is a max or a min, then f of C is called a relative max or min. Okay, so let's just draw a picture first just to make this really clear. So here's my xy plane, okay, and let's say I have a function that kind of does this. All right, and let's just say that let's just put my A right here, and we'll put my B right here. Okay, so it kind of doesn't matter. And remember now, A is this is an open interval, AB. So then basically between this point here and this point here, so this is the part of the function that we're interested in. So on that interval, there's a relative maximum here, right up at that point. Now it's not the maximum of the entire function, right? It's the maximum value between A and B. And there's a relative minimum here. Okay, so let's label these so we can get some good intuition about this. So you've got your relative maximum at this value, and you've got your relative minimum at this value. Okay, and the point being that, you know, we're talking about an open interval here, right? And so that's fine. Basically, what the open interval concept, what that kind of excludes is the possibility that the max or min is going to be like at an endpoint, right? So if the interval is open, so interval is a, b, open, basically that means that a and b are not relative max min, right? Because they're not in the interval, right? And so by having the interval be an open interval, that it kind of forces any maximum or minimums to be of this type, where you have like a peak or you have a valley. Okay. All right. So these are called relative max and mins. Okay. All right. So let's take a look at an example. Okay, let's take a look at an example and kind of try to flush out some of these distinctions here. Okay. All right. So let's consider the function f of x equals x cubed minus 3x squared. Okay. So then let me go ahead and draw it. Draw a nice, reasonably nice picture here if I can, so that we can see what this looks like. Okay, and so all of the action kind of takes place below the x-axis. So we'll say this is 1, 2, 3, 4, bigger than I was anticipating it to be, but so let me put this in: -1, -2, -3, -4, and then 1, 2, 3. Okay, 1, 2, 3. Okay, so the function kind of comes up like this to a maximum here at the origin, and then it drops back down, and it finds a minimum somewhere right around here, and then it comes back up. Okay, it doesn't necessarily look exactly like this, but the key thing is that we have sort of a minimum here and a maximum, relative maximum there. So we can intuitively see, right, that the relative max and min are, you know, located in these two positions. So this would be like a relative min here and a relative max there, right? And so notice, though, obviously, that these maximum minimum points are going to, like, if you think about what a tangent line would look like here at these points, you would have basically a horizontal tangent at the minimum, and then also, you know, at the maximum, you would have a horizontal tangent line as well, right? So a horizontal tangent lines at relative max mins. Okay, so you can kind of see that intuitively. That should make sense. And so what does that mean when you have a horizontal tangent line? Well, that implies that the derivative value at those points is equal to 0. Okay, so the maximum minimum points have a tangent line of slope 0, and that implies, of course, that the value of the derivative evaluated at whatever this happens to be, it looks like it's 2, is going to be 0, and whatever this one happens to be 0, it would also, the derivative would evaluate to 0 there as well. Okay, so let's take a look at that. So we have the actual function. This is a relatively decent drawing of it. Let's take a look at the derivative. So the derivative of this function, f of x equals x cubed minus 3x squared, we can quickly calculate that as 3x squared minus 6x. Okay, so that's the That's the value of the derivative. Okay, now if I want to know what x value is at this minimum and what x value is at this maximum, what I can do is I can try to find where the slope of the tangent line is 0. And basically the way to do that is to set the derivative equal to 0 and solve for the x values, right? So f prime of x equals 0 implies that you have 3x cubed minus 6x equals 0. Now, can we solve this equation? Yes, we can, right? So let's do that. So we'll do some factoring here. We'll factor out the 3x, right? And when we do that, we get x squared minus 2 equals 0, right? So let's just get rid of the 3. We don't need that. So x squared minus 2 equals 0. So that's kind of the sort of the kernel of this equation and solving this equation. So you've got I'm sorry. Yep, no, that's right. You've got one of the minimums is here at hold on one second. I think, yeah, okay, I'm sorry. Yeah, I was looking at this wrong. So one of the zeros is obviously x equals 0. And the other one is going to be found at, why do I have a, this should not be squared. That's right. So this should be 3x squared. Sorry, I knew I had a typo somewhere here. I was looking at this. So that's 3x squared minus 6x. So this should be a squared as well, right? So be careful of that. And so then when you factor out the x from both terms, you get 3x times x minus 2. So sorry about that. One of the zeros is at x equals 0. And the other 0 would be at what? X equals 2, right? Okay, so you've got these two spots where the derivative evaluates to 0. And does that square with our drawing? It does, right? So here, obviously, we said there was a relative minimum, which would mean that you have a horizontal tangent line, and that is x equals 0. Okay, so that's good. And then the other one we see is x equals 2, which is 1, 2, which is where this one is, right? And so here also, the derivative evaluates to 0, which means that that's that relative minimum. Okay. And then so what are those points? Well, we could figure those points out really easily. So we could evaluate f of 0, and we get 0 cubed minus 3 times 0 squared equals 0, of course. So 0, 0 is an extrema point. And then we could also evaluate f of 2, and so we get 2 cubed minus 3 times 2 squared. And when you crank all that out, what do you get? 2 times 2, so that's 8 minus 12, so you get negative 4. So another extrema point is at at 2, negative 4. Okay, so those 2 points, these are relative max-mins. Right, so we know, of course, that this is the relative max and this is the relative min. But then the question of how would you determine which one it is, we'll get to that in a little bit later. So there we go. So there's an example, just kind of working through, starting with a function. And in this case, we graphed it for some intuition, but you'll see that it's actually not necessary to graph the function to find those relative extrema. So let's take a look at another example. Okay. Let's take a look at this function. F of x equals 9x squared minus 3 divided by x cubed. Okay. So let's say we want to find the relative extrema of this function. Okay, so find relative extrema. Okay, so find whatever the peaks and find the valleys. So this time we're not going to graph it. We're going to just try to calculate it. We're going to try to figure out where they would be based purely on the derivative. And so let's calculate the derivative of this function. So d dx of 9 times x squared minus 3 over x cubed. All right, now this is a nice quotient rule problem. So it'll be low d high, so x cubed times d dx of 9 times x squared minus 3 minus high d low, like that. Okay, and then square the denominator like so. And running through this quickly, we can see that this derivative here, this is going to be 18x. Okay, and then minus 9x squared minus 3, and then this would be 3x squared. And the whole thing divided by x to the 6th power. Okay, now there's going to be some cleanup here, so let's expedite that, see if we can do that. So 18x to the 4th, and then minus, and then here you'll be 9 times 3, so 27x to the 4th, and then 81x squared, I believe. 9 times 3 times 3 is 81, positive, and then it's x squared, so plus 81x squared, and then the whole thing divided by x to the 6th. Okay, and we can combine these terms and we get negative 9x to the 4th power plus 81x squared over x to the 6th. Okay, and let's see, there's lots of things we can do here. Let's factor out 9x squared here. When we do that, we will get like 9 minus x squared, and then all over x to the 6th, and we can do a little bit more. We're getting close. Just try to get this down to like as reasonable. So maybe it'll be 9 times 9 minus x squared over x to the 4th. Okay, so that might be a good place to leave it. That's probably the best place to leave it. So remember, we're trying to find the relative extrema, so we need to solve f prime of x equals 0, right? Solve that for x. And so what that means is we've got 9 and then 9 minus x squared over x to the 4th equals 0. And so this guy can be kind of dealt with pretty quickly. Multiply both sides by x to the 4th and divide both sides by 9. And basically the important part here is the 9 minus x squared equals 0. The rest of it's all kind of stuff that's in the wind here. And so you can do a little algebra to see that this is negative x squared equals negative 9. So x squared equals 9. And so x equals plus or minus the square root of 9, which is plus or minus 3. Okay, so when we set the derivative of f, when we set f prime equal to 0, and we solve for x to find the roots of the derivative, this indicates that relative max and or min will occur at x equals 3 and x equals negative 3. Now we don't know if they're relative minimums or if they're relative maximums or which is which, but we just know that something interesting is happening at those points. So let me kind of draw what this function looks like here. And this won't be the greatest drawing, but hopefully it'll at least kind of clue you into what's going on here. So 1, 2, 3, 1, 2, 3, and 1, 2, and 1, 2. Okay, so we do indeed have an extrema at x equals negative 3, and we also have an extrema at x equals positive 3. Now what happens here, if you look at the function, f of x is asymptotic at x equals 0, right, because of the denominator. So what happens is the function kind of comes up like this, hits a maximum value here, pulls back a little bit, and kind of heads off We'll just say it does that. That's not important what it does too far out there. And similarly here, it comes down, hits a minimum, comes up, and heads off that direction, right? So you do indeed have relative max and relative min at these 2 points. Okay. Now we could easily plug in f of 3 and f of negative 3 into this function to figure out what the points are. And so if you plug in f of 3, I'll just tell you what you get. You get 2. Right? If you plug that into the original function, you get 2. And if you plug in f of negative 3, you get negative 2. And so this would be a relative max at 3, 2, right here. Okay, and then of course you've got a relative min at negative 3, negative 2, right here. And so that's basically what the derivatives revealed to us, just by setting the derivative equal to 0 and solving. Okay, so there we go. It's another good example. Okay, so let's take that and generalize even a little bit further. And what can we say now? So in general, a relative max or min will occur for a continuous function on a closed interval. So a relative max or min will occur for a continuous function on a closed interval at either the endpoints, right? That can happen, or at what are called, and here's kind of a definition here, critical points. We'll define this in a second here. Those critical points are those relative extrema that would occur only on the open interval. So those places where the derivative equals 0. Okay. Okay. So although this is actually technically a little bit incomplete as well, let's clean this up even further, right? So let's actually just throw out a definition for critical points. So let f be defined at C. Okay? If f prime of C equals 0, or if f is not differentiable at C, then C is called a critical point. Okay, sometimes people just call them critical numbers. It's the same kind of thing here. So let's just draw a picture here and see why do we need to extend the definition ever so slightly, right? So let's say I have a function that kind of comes up like this, okay, and then it turns back down like this, and then it goes like this, right? And so I've intentionally drawn these as this is by design. This isn't just not a smooth curve. This is actually a function that has a non-differentiable point here, right? So not differentiable, right? It's not differentiable there, and it's also not differentiable there. Okay, so in this plot, we can see that this point up here is denoting obviously a non-differentiable point on the graph, as is this point. right? And this point in this case would be a relative max. And this point here would be a relative min. Right, so if things like this are going to occur, if there's going to be this sort of non-differentiable issue, then those are going to tend to occur at relative extrema, right? So the function is going to, rapidly change directions or something like that. And so that's why we say let f be defined at c if f prime of c is equal to 0. Well, if it's, a nice, smooth, differentiable region and the derivative is 0, then that's the kind of relative max or min that we just looked at in the previous example. Or, if f is not differentiable at c, as we see in this example, right, these 2 points are non-differentiable, then those points are all called critical points. Okay. All right. Okay, so let's see here. So these, just to be clear, these are critical numbers, critical values. Right, so some of this terminology is very elaborate. So you get critical values, which inform whether or not relative extrema appear. You've got endpoints, open, close, right? So there's a lot of carrying on here. Let's see what's next. Let's do an example. Let's talk through. Actually, before we do an example, let's kind of like summarize some of this. Let's summarize some of this stuff here. So let's do some guidelines for finding extrema. On a closed interval. Okay, so step one. So for step one, right, the first thing you're going to want to do is you've got an interval, find the critical numbers, or find all of the critical points. In the interval. Okay, so find all the critical points in the interval, right? Like if you're trying to find the extrema, it's going to occur at either endpoints or at critical points. That's just the way it is, right? And so you need to find those values. The endpoints are given, right? If the interval is defined, right? So say I is equal to AB. Well, you know the endpoints automatically, right? But the critical points are not known, right? So you have to go find those. So first of all, the critical points could be anywhere that the function is non-differentiable, right? So that's an option. And then the other one is anywhere where the derivative is equal to 0. So let me put those in here. So non-differentiable points satisfying f prime of x equals 0, right? So that's basically your critical points. All right, step 2 then, right? So once you've figured out all your critical values, you want to evaluate f at each of these critical points. So evaluate f at each critical point, right? So you need to know the value. Remember, you're trying to find maximums and minimums. So you need to evaluate f of x. You need to figure out the value of f at each of the points. So that's step 2. And then, don't forget to evaluate f at the endpoints of the interval as well, right? So those are technically not what we call critical points, but they could be the relative. You could have extrema there. All right, and then of course, obviously, you've got a bunch of evaluated points. The least is the min, and the largest is the max. Okay. Very good. There we go. Right. So these are guidelines, right? And so let's do an example kind of following this procedure. Let's see where we get. Okay, so let's do an example. So example, find the extrema. We want to find the extrema of this function, f of x equals 3x to the fourth minus 4x cubed on the interval -1, comma 2. So -1, 2. So first of all, let's find, this is a polynomial, right? So there's no issue with non-differentiability here, right? So all of these points are going to be, this is a smooth, continuous function, nothing to worry about here. So no non-differentiable points. Something to note. Okay. So let's go through and find the critical numbers, the critical values that pertain to zeros of the derivative. So let's calculate the derivative here. And so the derivative is 3 times 4 is 12x cubed minus 12x squared. Okay, so real easy to calculate that. And set the derivative equal to 0, f prime of x equals 0. That implies, right, that 12x cubed minus 12x squared equals 0. Okay, can we solve this for 0? Or solve this for x, sorry. Yeah, let's go ahead and factor 12x squared out. All right, so we take the 12x squared out, and what am I left with here? X minus 1 equals 0. All right. So I've got kind of two pieces here. So the first one is the 12x squared equals 0. Well, that just means that x equals 0 is a root. Okay, and then the other one is x minus 1 equals 0. So x equals 1 is a root. Okay, so I've got some critical numbers. Good. So x equals 0 is a critical number. X equals 1 is a critical number. Okay, and so let's see, let's kind of summarize what I have here. So right, step 1 was to find all the critical numbers. We've done that. Now step 2 is then going to be to evaluate all of them. Evaluate f at each of the critical points. So let's put everything together here. So you've got the left endpoint, which is -1. I'm going to write that in here. Okay, I've also got two critical numbers. So I've got x equals 0, which I found right here. And I got another critical number, x equals 1, which I found right here. And then I've got the right endpoint. Right, and the right endpoint was x equals positive 2. Sorry. Okay, so let's figure out what f is equal to at each of these. Well, if I plug this in, I'm just going to kind of done the work off to the side here, but f of -1, so if I plug that in, I will get, altogether, I get a 7 here. So the value of the function at -1 is 7, and then f of 0 is 0, f of 1, right? So remember, I'm just plugging in 1 into the original function here. So if I plug in a 1, I get basically a -1. And if I plug in a 2, I get 16. Okay, so what is this telling me then? Well, the smallest is here, right? So this would represent the min on this interval. And then the maximum value is here. Okay. And so what I'm saying, well, I guess what we're saying here is that we have a relative min. Well, let's not call it relative min. Let's call it a minimum at the point 1, -1, and a max at the point 2, 16. Okay. Sometimes when we say relative min, that sort of implies that we're talking about, just the peaks and valleys. But absolute max and mins on intervals are going to include the endpoint of values as well. So what does this function look like? Well, I went and plotted it or looked it up or something. And so somewhere over here you've got -1, 7 on this endpoint. And then this is not to scale, but you got 216 on this endpoint. 0, 0 is here. And then 1, -1 is here. Again, terrible drawing. But basically the function kind of comes down like this, flattens out at 0, 0, then drops down to here, flattens out, and then comes up. So it looks like this. Right, so clearly you do have a kind of a minimum value here, and you have a maximum value on this endpoint. Right, so this would be the endpoint of 2, and this would be the endpoint of the interval of interest at -1. Okay, so very nice, right? So we're able to basically identify all of the kind of high points and low points of the function on this interval purely analytically without even like drawing a picture or looking at a picture, right? And we can get very good results doing that. So that's the power of just kind of interpreting the derivative and then kind of thinking through what sort of the logical implications of the derivative equaling 0, etc. Let's do one more example. Maybe we'll do 2 more examples. Let's do this one though. F of x equals 2x minus 3x to the 2/3 power. And again, we're looking for mins and max on the interval -1, 3. Okay, so you've got this interval, -1, 3, and this function, and our task is to find the extrema, so the extreme points. Okay, well, we're going to follow the same procedure as the last one. So the derivative here is equal to, d dx of 2x minus 3x to the 2/3 power, which is 2 minus 3 times 2/3 to the x to the -1/3, like so. And so that means that the derivative, we can clean this up a little bit. Let's write it as 2, the 3's will cancel, minus 2 over x to the 1/3 power. So that's what this one looks like. I think we can write it better. Let's write it like this: 2x to the 1/3 minus 2 all divided by x to the 1/3. Now what did I do there? I just multiplied top and bottom over here by x to the 1/3 to get a common denominator. This is better, and the reason this is better is because we're going to set this equal to 0 and solve for x, right? So f prime of x equals 0. So that means this guy here, 2x to the 1/3 power minus 2 over x to the 1/3 power equals 0. Can we solve this for x? Yes, we can, right? So multiply both sides by x to the 1/3, divide both sides by 2. Actually, hold on. Let's do it in 2 steps. So 2x to the 1/3 minus 2 equals 0. Then you do have to factor this first technically, right? So you'd have 2, and then it'd be x to the 1/3 minus 1 equals 0, and then divide by 2. So x to the 1/3 equals 1. And now how would we solve for x in this case? How would we get x? How do we negotiate the exponent? Well, we basically cube both sides, right? So you can think of it like this. And so if we do that, we get x equals 1, right? So we have a critical number at x equals 1. Okay, so this is a critical number. Okay. Are there any other critical numbers that we need to worry about? Well, yes, because remember the derivative here is f prime of x is equal to 2x to the 1/3 minus 2 over x to the 1/3. So we do have an issue here at 0 as well, right? So the derivative here is not defined at x equals 0, right? And so what does it mean when the derivative is not defined? Well, it just means that f is not differentiable at x equals 0, right? So another critical number would be x equals 0. Okay, so you've got x equals 1 as a critical number, and also x equals 0 is a critical number. So you got those two. One of them is a critical number because it's not differentiable. That's x equals 0. The other one is a critical number because it's a root of the derivative, and that's x equals 1. So let's, again, kind of plug in everything that we know here. And I like to do it this way because it makes kind of the analysis like hard to mess up. So you plug in the endpoint first. And then critical numbers, I like to just rank order them here in the middle. So you've got a critical value at x equals 0, right? That's the non-differentiable point. You also have a critical value at x equals 1, right? That's the root of the derivative here. And those were the only two critical values we found. You could have more, right? But not for this function, but functions could have hundreds of critical values. I mean, probably the examples we'll do in this class will not, but and then you've got the right-hand endpoint, which is x equals 3. Okay, so very good. So you've got these different values, and these are the values where you're going to have a min or a max if you do have one. So now just figure out which one is the min and which one is the max. So plug all of these into the original function. So very important to keep in mind what you're doing here, right? So if I want to know if this is if I want to know if x equals -1 is a min or a max, I need to know what the value of f is at x equals -1. So I have to plug -1 into the original function. Now be careful here, because a lot of times people will try to plug f equals -1 into the derivative, right? That would not be helpful, right? That's just going to tell you the slope of the function at -1. It's not going to tell you anything about the minimumness or the maximumness of the original function. So you need to plug it into the original function. And just off to the side, you can evaluate that really quickly. But you get -5 for x equals -1. And then f of 0 gives you 0. F of 1, when you plug 1 in, you get -1. And finally, when you plug in f3 into the function, you get kind of a decimally number or a rational number. Depends on how you evaluated it, but 0.24, we'll say something approximately like that. So you can easily look at this and say, okay, the minimum is here. The maximum, it turns out, is here. Okay. And then at this point, you just, pull out your graphing calculator, graph the thing, take a look at it, or go, dial the function in at Wolfram Alpha or something and see what it looks like. And so when you do that, this is what it looks like. So down here at -1, -5, you do have a minimum. And then the function does is it comes up to 0, 0. And this is the non-differentiable point, because the function acts really funny here, and it kind of comes back down and goes like this. And it approaches the x-axis, but it doesn't quite get there on this interval anyways. And so down here you've got 1, -1. This is 0, 0. And this point here is 3, -, 0.24, right? So it's real close to 0, but not quite. And so this is what the function looks like. And so, yeah, you can see that here's the max. And for this interval anyways, here's the min. Right, remember, this is all to do with this interval. Right, so the function obviously would have values that are smaller if you wander outside of this interval, but so long as your concern is this interval, then you do have the max here and the min here. Right. So yeah, it's good to reflect on the fact that we found these points without graphing anything, without having to plot anything, or without any of the usual things that you would want to do to find minimums and maximums. Right, so all we did was evaluate the derivative, also look for non-differentiable points, and then evaluated the endpoints. And from that, we were able to determine the mins and the max really quickly. Okay, excellent. I think we'll stop there. And so that's what we mean when we say extrema on an interval, right? And so then next time we'll get into something called the mean value theorem, which is kind of an extension of this idea. See you then.